Hey, I'm so excited that I can bring this video to you. In this video, I'm going to answer 3 questions. Number 1, how does an aircraft have the lift to balance the weight of all the people, the aircraft, and the cargo? Number 2, why does a spinning ball curve? And number 3, what's the minimum area that's required for the wings of a Boeing 747 to stay in the air? Now, let me explain what you just witnessed. I had these 2 books set up and I was blowing air right below it. So the speed of airflow below the paper is much higher than the speed of airflow over the paper. Now, over the paper, technically, the air is not moving. And so, according to Bernoulli's principle, which I'm going to prove to you soon, where the speed of flow is bigger, there the pressure becomes lower. So that's the whole idea used for attaining the lift of an airplane and to explain why a spinning ball curves. And now, on top, the velocity is 0, the pressure is high. At the bottom, the speed of airflow is much higher, so the pressure is low. And according to Bernoulli's principle, a flowing fluid has 3 types of energy. And the sum of all these 3 energies must be constant at any point. So when you take the point below as 1 and take the point above the paper as 2, and you take the total energy below and above, they must be equal. That's what has come up now. Now in this one, the first one is the pressure energy, second one is kinetic energy, and the third is potential energy. Now we know that kinetic energy is 1/2 times mass times velocity squared. And so density appears here because I've divided the mass by volume. And you know that mass by volume is density. Same thing here, potential energy is mgh, and when you divide mass by volume, have density. Now, one word about pressure energy. Pressure energy is actually the product of pressure and volume. And when you divide by volume, the volume vanishes. So this entire equation is written for 1 meter cube for unit volume because I've divided all the 3 terms by volume. So the total energy below the paper is equal to the total energy above the paper. Usually we consider points at the same height, which means the potential energies are equal. And so we can leave out the term for potential energy if H1 is equal to H2. For example, if the aircraft is flying at the same horizontal level. So in that case, you see that that term vanishes, and now it's very easy to understand that if V1 here is greater than V2, then P1 has to be less than P2 for the total to be the same on either side. So that's why we say that where the speed of flow is higher, the pressure is lower. Now, how does this apply to the lift of an airplane? What you see in the diagram is the profile of the wing of an airplane. So you see that the bottom part of the wing is flat while the top part is curved. So remember, that's the wing of the airplane, and the view is along the tip. So that means along the length of the wing. So you're seeing the top part curved and the bottom part flat. So as the aircraft taxis on the runway, The wind hitting the wing divides into two parts. One part goes below the wing and the other part above. And since the path length on the top of the wing is greater, the speed of flow above has to be faster. And where the speed is faster, the pressure is lower. Okay, so that's the simple idea. The air that splits here has to recombine at the other end because of the equation of continuity, where mass cannot be created or destroyed. In order to do that, the air flowing over the top of the wing has to flow faster because that length of the path is bigger. And when it flows faster, the pressure becomes lower and the aircraft gets the lift. All right, so now let's apply Bernoulli's principle at these points 1 and 2 and try to find out a formula for the pressure acting from which we can get the force of lift on the wings. But before we do that, let me also tell you that the body of the aircraft also provides a certain amount of lift, and the engines, because of the thrust, will also provide a lift. So we're not considering those two factors here. And this formula only gives the lift because of the wings of the airplane. So here we go. We try to make P1 minus P2 the subject because we're trying to find the difference in pressure between points 1 and 2. And now in order to do that, you bring P1 minus P2 to one side and you get this formula, rho by 2 V2 squared minus V1 squared, where V1 is the velocity of flow below the wing and V2 is that above the wing. Now once you get the pressure difference, we can find the difference in force or the lift, because force is pressure multiplied by area. So to get the force, all you got to do is multiply this with the area, the total area of the wings, and you would get the force. Now substituting P1 minus P2 will give us, substituting this entire thing, you're going to get the force as A rho by 2 V2 squared minus V1 squared. So we can calculate the lift by knowing the area of the wings, the density, which is the density of air, and the two velocities. So let's do that. By rule of thumb, the force required per meter squared is 1000 newtons. So we're going to assume that the force of lift is 1000 newtons on 1 meter squared of the area of the wing, and we're going to calculate the velocity difference between the top and the bottom. Rho is 1.29 kilogram per meter cube. That's the density of air. V1 is 60 meter per second, which is about the value when it's taxiing. So this is when the aircraft is trying to take off. And from the formula, we will calculate V2. In order to do that, just substitute the terms and rearrange. So the force is 1000. The density is given and V1 is given, so we can find V2. So when you do all the math and take the square root, you are going to find that the velocity above the wing is 71.8 meter per second. So that's during takeoff. Now let's do the same thing when the aircraft is cruising at a height, usually about 30,000 feet or higher for commercial aircraft. And at that point, the density of air is not 1.29, it's going to be much smaller. So it's cruising and it's at that height, so now the velocity of air below is 245 meter per second. The density has been reduced to 0.3225 kilogram per meter cube, and now we're going to find V2 again. The same formula, substitute into that and calculate. Again, we are just going by the rule of the thumb that 1,000 newtons is required for every meter squared. That's why we have 1,000 right there, and then you rearrange this and you find that the velocity over the top of the wing is 257 meter per second. 257 meter per second. So this is how the aircraft is able to stay afloat. Next, here are some real practical numbers to do with the Boeing 747. We're going to work with the maximum weight at takeoff for a Boeing 747. It's coming up right now. It's 412,769 kilogram. That's the mass. Now, to get the maximum weight, you got to multiply this with 9.8, which gives this big number, 404,5136.2 newtons. And then, in order to get the lift equal to this weight, because we know that the lift must be equal to the weight, the approximate area of the wings can be calculated to be 4,045.1362 meters squared. That's huge. That's why the wings of a Boeing 747 are that big. Again, remember, we have not considered the lift on the body of the aircraft, neither have we considered the lift due to the thrust of the engines. Next up, let's use Bernoulli's principle to calculate the force acting on the roof of a house. We're considering flat roof here, not curved, flat roof. And we also know that the air inside the home is technically not moving. So the velocity of the air inside the home is 0. And let's assume that due to winds, fast winds flowing on top of the roof, the velocity is much higher. We're going to assume 35 meters per second. And using this, we can calculate the force on this flat roof. Just the same formula as before, which we've been using. We can calculate the force on the roof using this formula. Again, rho A by 2, V2 squared minus V1 squared. Rho is the density of air. Again, 1.29. And the area of the roof is assumed to be 245 here. Okay, that's why you see this number here. The area of the roof is 245 meters squared. And we find the force on the roof to be 1.94 times 10 to the 5 newtons. That's a huge force. Well, I hope you enjoyed the animation where you could see that with the spin, the ball curves a little bit more than it would have done under the action of gravity alone. So we're assuming clockwise spin, and when the ball spins, the air around the ball is moving in the same direction, in the clockwise direction. But the forward motion of the ball makes the air flow above the ball and below the ball, as you can see. So the forward motion of the ball makes the air flow above the ball and below the ball, while the spin motion of the ball makes the air flow in the same direction. So when you look at this diagram carefully, you understand that the flow of air on top is in opposite directions. Due to the forward motion, air is flowing backwards, as you can see, backwards, while the spin motion, it's flowing opposite. But below the ball, both the forward motion and the spin take the air in the same direction. That means the speed of air flow below the ball is higher. And where the speed is higher, the pressure is lower. That's why the ball curves and hits the ground at B instead of at A. If the ball had not been spinning, just because of the action of gravity, of course it would have hit the ground at A. But because of the spin, it hits the ground at B. That's why the batter, who may not be able to guess the spin direction, swings the bat above the ball and misses it. Now, I hope you understood Bernoulli's theorem and its applications. I mean, it's very interesting. There are many other applications of Bernoulli's principle. I look forward to other videos that will be coming out in the next few weeks that will really deal with practical applications of physics. Now, I'm trying to get people interested in physics, and so do me a favor, like the video, comment on the video, and share it so other people can get interested in physics and become great innovators, scientists, and engineers. Thank you for doing that. See you on the next one.